Well, good afternoon. Today we're going to be talking about limits of polynomial and rational functions and whether they are continuous and how to find those limits. So first off, the theorem of polynomial functions says that polynomial functions are continuous for all x. Remember, a polynomial is basically a equation where there are no variables in the denominator, all of them in the numerator. And the second theorem would be for rational functions. That's where we do have variables in the denominator. And they are continued for all x for which the denominator, q, would not equal 0. So hopefully those are things that you are already kind of familiar with. All right, so today we're going to be doing two things. First off, we're going to be evaluating the limit. And then secondly, deciding if that function is continuous at that particular spot. So, for example, we got this limit as x approaches 5 of x squared minus 25 over x minus 5. And we can see that this is not defined at x equals 5, because x equals 5 would make the denominator a 0. So right there, that kind of answers our continuous question. No, this is not going to be continuous, because the answer is undefined at x equals 5. But we can still find the limit at x approaches 5 by doing a little factoring in the numerator. And again, this is one you're just going to have to be good at. You have to recognize, that anytime you have an a squared minus b squared type of number, that you can factor that as a plus b and a minus b. So again, that's just going to have to be something you start to recognize if you don't already. So I was able to factor the numerator, cancel out those x minus 5s, and I can see that the limit as x approaches 5 equals 10. If you were to graph this, what you would find is that you've got this, essentially this intercept at 5, a slope of 1, and what's going to happen here at 5 is that there's going to be a hole. And that's what's going to happen in this graph. So it's undefined at that spot because of the hole. All right, but that's what the graph would look like. So then when it says, is the function continuous at x equals 5, then the answer would simply be no. It is not continuous at that spot. There is a hole in the graph. So let's do another example. So we're looking at this one here. Again, we got another rational function. So because it's a rational function, we can already probably assume that we're going to be not continuous because there's something that could make that denominator a 0, which is what we're looking for. So the limit as x approaches 0. If you just plug that 0 in, you will see that in the denominator we're going to get a 0. So this is not going to be continuous. All right, so we can tell that right away. It's not continuous. Oops, if I can spell it right. Not continuous at x equals 0. All right, so we got that piece taken care of. So let's actually find the limit. So to find the limit, we're going to first off try to do a little factoring. See if we can do some things to cancel out the x from the denominator. Well, both terms in the numerator have an x, so I can factor out a common x. And then the denominator, there's only one term, but I factored out the x anyway. Just kind of rewrote it in that order so you could see that those x's would cancel out. Essentially now leaving me the limit as x approaches 0 of x plus 3 over 2. Now that I don't have a variable in my denominator, I can actually just plug in the 0 and evaluate. So there's my answer. 3/2 or 1.5 or 1.5, but it's not continuous at x equals 0, and the reason would be because of that rational function there. All right, so again, kind of a two-part problem today. You're first off checking to see if it's continuous, and then seeing if you can find the limit at that spot. All right, best of luck today.